What happens if you just keep cutting in half? Let's start with an apple and a really, really sharp knife. You take the knife in your hand, and with a flourish, you slice the apple into two neat pieces. The apple halves become quarters, then the quarters become eighths. In front of you are smaller and smaller pieces of pulpy white apple. But by your 14th cut, a regular rectangular pattern emerges, and you realize the smooth apple flesh is built out of an array of plant cells. You keep on cutting, chopping the cells into smaller and smaller pieces. Another 8 cuts reduces the cells into complex molecules of carbon, hydrogen, and oxygen. With a few more cuts, what was once the apple is now 10 quadrod-set individual atoms. Is this it? Can you cut no more? But your knife is incredibly sharp, and you begin to chop into the atom. Peeling away the cloud of electrons, you reveal the seeming nothingness, with almost nothingness, for at the center sits the tiny atomic nucleus, 100 trillion times smaller than the apple that you started with. But again, you are undaunted, and again you continue chopping. The nucleus splits into protons and neutrons, the protons and neutrons into quarks and gluons, and you find yourself in the ethereal world of the subatomical world governed by fuzzy probabilities. The apple, now nothing but an ethereal wave upon a sea of fields, feels like it has finally reached the limit, the fundamental pieces of the universe, though some say you can keep going. After more than 100 cuts, point-like quarks and electrons might be revealed to be waving strings, a trillionth of a trillionth of a trillionth of a meter across, vibrating across extra dimensions. Down here, maybe even space and time are chunky, fundamental blocks that can be cut no more. Or maybe any semblance of reality will melt away as we find that our universe is truly a simulated cosmos, churning away on some superdimensional computerer that our three-dimensional existence is nothing but an illusion, and everything we know and love is shown to be a hologram. Or even more strangely, maybe it's just raw mathematics all the way down. But which is true? And how can we be sure? To understand reality, the true nature of reality, and how humans, over thousands of years, have struggled to unravel it, we are going to have to dissect the cosmos and ask some very difficult questions. Is the apple real? You can hold it, smell it, taste it. You can see the greenness of its skin in the sunlight. Surely, the apple is real. But what does it mean to be real? Just what is reality? Isaac Newton used to bookmark the pages in his books in a very specific way. He would turn the corner of the page down onto the phrase, or even the word, he wanted to remember. Of course, it was easier for him to concentrate, as he had no mobile phone determined to distract him or suck him into endless doom scrolling. And so, our sponsor today is the perfect learning tool for our modern age. If you care about building a life of learning, Imprint is the app for you. If you haven't used it before, you probably haven't seen anything like it. It provides bite-sized lessons that take only a few minutes and are beautifully illustrated and animated, creating a highly visual, effective, and interactive learning experience. Their library includes courses, book summaries, and quick-read articles on topics like psychology, philosophy, physics, productivity, science, history, and many more. I personally have been enjoying Carlo Rovelli's dive into the mind-bending physics of time. Another exciting option I've been looking through is Thinking, Fast and Slow by Daniel Kahneman, which helped me understand my own cognitive biases. Now is a great time to try everything Imprint has to offer free for a full 7 days by scanning the QR code, visiting imprintapp.com, Universe, or clicking on the link in the description. Plus, as fans of the entire history of the universe, you'll get 20% off an Imprint Premium subscription. To our truly ancient ancestors, reality must have been obvious. From the plains of Africa to those wandering the snowy wastes of northern Europe, reality was what you sensed with your eyes and ears, touch and tongue. Reality was simply out there. The snap of a twig in a forest might tell them that their next meal is at hand, or warn them that they might be on the menu for a beast with bigger teeth and sharper claws. Sensing reality was a matter of life or death. Perhaps, therefore, in their day-to-day struggles, these truly distant ancestors had little time to wonder, little time to think deeply about the world that surrounded them. But as the human mind developed and thoughts expanded, the nature of reality surely changed as well. We know humans began to bury their dead almost 100 years ago. Quite what they were thinking as they bid farewell to their loved ones, we'll never know, but perhaps they were thinking of a world beyond our reality, an afterlife. These ceremonies provide insight into human thought, and that there was more to reality than meets the eye, or ear, or nose. Ideas around spirits and gods and invisible yet powerful influences began to emerge, along with questions of meaning and purpose. And of course, the gods also gave us the apple, providing delicious fruit for us to eat. There was no need to question the reality of the apple beyond this. The answer was simply beyond the ponderings of the human mind, only found in the thoughts of the gods. But others began to wonder more deeply. Plato was one of the greatest philosophers of the ancient world, living in Athens in the 4th century BC. His real name was Aristocles, with Plato being just a nickname that meant broad and apparently referred to his stocky build. The material world bothered Plato. Where do objects get their material properties, be it the greenness of the apple skin or the fact that dogs have 4 legs? Our world, Plato contended, was not the real world. And to understand this, we will have to explore his famous allegory of the cave. In this cave, a group of prisoners are kept chained, staring at a wall. The prisoners have always been there, chained in the cave, and have never been outside to experience the real world. All the prisoners can see is the wall in the cave in front of them, but on the wall they see shadows. These are formed by sunlight streaming into the cave entrance as people go about their daily business at the mouth of the cave. What are they to make of this external reality, one that they can barely see? How are they to understand the real world? But we can go further. What if they are not really seeing shadows of reality from beyond the mouth of the cave? What if, instead, some mischievous people have blocked off the cave entrance and are illuminating the prisoner's wall with a bright fire? With this light, these people can now play mind games with the prisoners, using shadow puppets to play out stories on the wall. No longer are the prisoners simply seeing people wander by the cave entrance. Now they can see stories of monsters and battles, castles and kings. What are the prisoners to make of this new reality? Is it any less real than before? To them, this image on the wall is their reality, there is nothing else. And so, these exciting new tales are as real as the previous shadow people milling about. To them, the monsters and battles are truly real. Plato then asks us to consider that we are like the prisoners, and the reality we experience every moment of the day is a projection of a place where true reality plays out, with our imperfect world being a shimmering image of perfection. To Plato, our experiences are just shadows of a true reality. Considering what we know now, this was oddly prescient. But for the story of reality, this was just the beginning. For to reveal the secrets of the universe, to unveil the ultimate truth of the nature of the cosmos, the answers did not lie in the hands of the gods or ancient philosophy. Instead, we would have to delve deep into the fundamental makeup of matter, time, and space. We would have to turn to the insights into reality provided by scientific exploration. And when we did, things quickly got very strange indeed. Philosophy will clip an angel's wings, conquer all mysteries by rule and line, unweave a rainbow. In the first few months of 1821, the poet John Keats died in Rome. He was young, only 25, but his body was racked by the scourge of tuberculosis. In his short time, he was prodigious, writing on the natural beauty of the world around us. And like many before and after, he was only truly recognized after his death. Keats was born almost 70 years after the death of Isaac Newton. It was the time of the Industrial Revolution, a revolution driven by Newton's insights into the natural world. The scientific revolution of Newton and his contemporaries had sought to peel back reality and reveal it as nothing more than a manifestation of physical law in action. And finally, it had been Newton who had realized that the white light of the sun contained all the colors of the rainbow, and that water droplets in the sky spread sunlight in a glorious display from red to violet. The seemingly mystical appearance of one of nature's true wonders had, Keats complained, been destroyed by Newton, reducing it to little more than a prism. In Keats's words, Newton had tried to unweave the rainbow. Newton's triumph might have been Keats's lament, but as Newton began to unweave the nature of light, he kick-started a long tradition of science, peeling away the very nature of reality to expose its bones. Let's think again about our apple. Of course, one of the defining characteristics of a ripe apple is its colorful skin. But just where does this color reside? Apples are made of a complicated mix of water, sugars, and more complex structures, so why do we see the apple appear green? To answer this question, we must delve deeper into the meaning of color. And the story begins with the last man who knew everything, Thomas Young. Thomas Young was born in the tiny Somerset town of Milverton in 1773. Precocious from the very start, he learned French, Greek, Italian, Latin, Aramaic, Persian, and more, and was instrumental in deciphering Egyptian hieroglyphics soon after the discovery of the Rosetta Stone. For some of you, Young's name might already be familiar, as it was Thomas Young who undertook the first of what's known as the double-slit experiments. We will return to Young's double-slit experiment later in our story. Artists knew that mixing colored paints produced new colors, and three colors, red, green, and blue, seemed to be particularly important. Young proposed that the eye contains three kinds of fibers we now call cone cells. One kind is sensitive to red, another to green, and another to blue. The amount that each kind of cell is stimulated is passed along the optic nerve into the brain, where it is mixed, like paint in the mind, to give us the sensation of color. Things, however, get weird when we look at the eyes of other animals. Our closest relatives, apes and monkeys of the old world, are similar to us, sensitive to three color bands. But most mammals only have two, equivalent to our blue and green. This must reduce their color palette. Would they see a banana as being yellow? Bees have three color receptors, one sensitive to blue, another to green, and yet another to ultraviolet. Reptiles, fish, and birds can have four or more color receptors. Indeed, the small but violent mantis shrimp has a total of 12 receptors spread across the rainbow. These animals must see the world in an array of colors that we can't even begin to imagine. And so, what are we to make from this confusing array of animal visions? For humans, the yellow of the rainbow matches the stimulated signal from the skin of a banana, but other creatures probably wouldn't agree. To them, maybe a strawberry, or broccoli, or human skin is the same color as a banana. This tells us something deep about the nature of reality. Our sight is nothing but a shadow of reality, created by our brains. It is subjective, not objective. We live in a visual simulation of our own making, built from stimulations being fed into our brains. Newton told us about raindrops and sunlight, but the colors of the rainbow only exist in our minds. The sounds that we hear are similar illusions, an interpretation in our minds of vibrating eardrums due to waves of pressure in the air. We live in a virtual reality of our own making. So if what we perceive is not truly reality, then what is? Well, space and time can at least be trusted. The apple is here and now, that is one certainty. Or is it? For in the revolution that was to follow Newton and Young, no part of reality was safe. Time ticked by slower in the past than today, and in 2023, astronomers measured just by how much. Their focus was quasars from 12 billion years ago, black holes weighing billions of times the mass of the Sun. Swirling in the intense gravity of these black holes, matter orbits at close to the speed of light. This matter is heated to billions of degrees and glows intensely, visible across the universe. But in the turbulent maelstrom, before it vanishes into the hole, matter crashes and grinds, and the intense light brightens and fades like a cosmic firework display. Hidden in this flickering, astronomers found a subtle pattern, a special regularity, and they realized that they could use this quasar tick to measure the passage of time when the universe was young. These astronomers compared the tick of a clock today to the ticks of these quasars, finding that the farther away the quasar, the slower and slower these quasar ticks became. And when the universe was 1/5 of its present age relative to today, time was ticking at 1/5 its current rate. This result was spectacular, but it was not unexpected, for this cosmic dilation was written into the mathematical laws that govern the universe, in a theory developed more than a century before. A theory that forever changed the reality of space and time. I think, therefore I am. It was the French philosopher René Descartes who uttered these famous words, and this deep musing on the reality of being has reverberated throughout the centuries. But Descartes stared into more than just the meaning of existence. One night, in 1000, 619, Descartes shut himself away in a small room to avoid the cold. As a mercenary fighting for the Dutch Protestant state, he had studied engineering and mathematics, but this frigid night would be like no other. The story goes that Descartes, confined to his sickbed, lay staring aimlessly around the room. He spied a fly walking across the ceiling before launching into flight, darting about and settling on the wall. As the fly buzzed about from ceiling to wall and back again, a thought wandered across Descartes' mind. How could he describe the journey of the fly? He realized that he needed a reference point to anchor the motion of the fly, and while this point was arbitrary, it must be consistent and not change. He also realized that simply talking about the distance from the reference point to the fly was not sufficient. As well as the distance, you needed the direction to fully describe its motion. Then a startling thought came to Descartes, a realization that would simplify the fly's motion. For his point of reference, Descartes took the corner of the room where two walls met the ceiling. From this point, he imagined lines running along the joins, defining axes that meet at right angles. If you project the fly's location onto each of these axes, Descartes reasoned, you get numbers, and it is these three numbers that you need to specify the location of the fly at any instant. Three numbers to uniquely define a location in three-dimensional space. Three numbers that change continuously with the ticking of the clock. Descartes' coordinate system seems obvious to us today. Children are taught to use it when they first encounter location and motion in elementary science. For professional scientists, laying down a Cartesian coordinate system is the starting point of finding solutions, and so Descartes' name continues to reverberate throughout the centuries. Dying in 1650, Descartes was unaware of a young boy growing up in the English countryside. This boy, Isaac Newton, would grow to use these notions of time and three-dimensional space, laying them down as the mathematical stage on which all motion takes place. It was Isaac Newton who laid out the rules that we now call classical mechanics. In Newton's universe, time is a true absolute, a single clock that ticks across the universe, a tick that everyone agrees on. Space was slightly more complicated, as Descartes' contemporary Galileo had discovered, since each observer has the freedom to define the origin of their own coordinate system. Galileo thought more in terms of stories than in the mathematics of Descartes or Newton, and he laid out his notions of motion through thought experiments. Thinking about being aboard a ship, he realized that if the ship was in a harbor or sailing smoothly on a glassy sea, then the experience below deck would be identical. However, if the wind picked up and the ship began to accelerate, or if it sailed into choppy waters and began to rock and roll, then those below deck would feel this change in motion, as plates and cutlery slid off tables and people became unsteady on their feet. From this, Galileo declared that there must be no absolute rest in the universe. All motion, he said, must be relative, and the laws of motion must be the same for observers in a state of unaccelerated motion. The first theory of relativity had arrived. These ideas are reflected in Newton's equations of classical mechanics. Every observer in uniform motion can use Newton's three laws to calculate the outcomes of experiments. It's easy to test this yourself. Drop a ball on a train station platform and watch it fall to the floor. Repeat the experiment on a train traveling at constant speed, and again the ball will simply fall straight down. However, if you drop the ball at the start or end of the train journey, when the train is accelerating up to speed, or slowing down as it approaches its destination, the ball will veer toward the back of the train, or the front of the train, seemingly defying Newton's laws, as no forces are pushing in these directions. These fictitious forces only appear because your coordinate system is accelerating, and they vanish as soon as you achieve uniform motion. This picture of the background of reality, a rigid stage of space and time, existed for several centuries. But then, a Scottish physicist, James Clerk Maxwell, finally unraveled the mystery of light, and with it, the bizarre reality of our universe. Maxwell's impact on science was enormous. By the mid-1800s, Maxwell had mathematically united electricity and magnetism. There had been experimental clues that these strange phenomena were related, but in a handful of beautiful equations, Maxwell showed that electricity and magnetism were not two separate forces, but one and the same. This was already an immense achievement, one for which Maxwell would become scientifically famous. But he looked deeper into his equations and realized that they implied something even more profound. Light itself must be an electromagnetic phenomenon, a self-propagating wave of oscillating and intertwined electric and magnetic fields. His equations even revealed the speed of light, a blistering 300 kilometers per second. But curiously, they said nothing about what this speed was relative to. By whose coordinates was this speed determined? It seemed that to save physics, a notion of absolute rest would be needed. Some had proposed that there existed an invisible, all-pervading medium, an ether, through which light propagated throughout the universe. Physicists designed clever experiments to detect motion through this ether, such as bouncing light rays off mirrors or sending currents through circuits and lighting bulbs. If the Earth moved through the ether, these experiments would show measurable effects. But they did not. The outcomes of these experiments were the same. No matter the motion of the Earth, a serious headache for Galileo's idea of relative motion. Why would electromagnetism know about an absolute state of rest, while the rest of physics mechanics, for example, didn't seem to care? Why would Galileo's relativity hold for everything except electromagnetism? Why would the laws of physics be so complicated? In 1905, one physicist stated that it didn't have to be so messy. The universe, he said, was not split into two domains, one where Galileo's relativity applied and one where it didn't. No, electromagnetism had to respect relative motion, too. And so, at the start of the 20th century, Albert Einstein's special theory of relativity was born. At its core, special relativity reflects the dream of the lazy physicist, the dream of explaining as much as possible with as little as possible. Einstein demanded that all observers, irrespective of their relative motion, must be able to use Maxwell's equations to predict the outcomes of electromagnetic experiments. But this simple demand came with a profoundly uncomfortable consequence. All observers must measure an identical value for the speed of light. This was simply not possible under Newton's notions of absolute space and absolute time. Therefore, Einstein concluded, space and time themselves must be flexible. Times and distances must depend on who is observing them. This sounds like lunacy, and indeed, it is not the experience of our everyday lives. But experiments conducted near the speed of light reveal the distortion of space and time beyond any doubt. In the 1960s, irrefutable evidence for the twisting of time was found. The focus was on a subatomic particle known as a muon, effectively a heavier version of the electron. But unlike the electron, which lives forever, muons are short-lived, lasting only about 2/millionths of a second before disintegrating into electrons and neutrinos. Physicists knew that high-energy muons were constantly created in the upper atmosphere when particles from deep space cosmic rays smashed into gas molecules. Traveling close to the speed of light, these muons should have only survived for about half a kilometer before decaying. Yet physicists detected muons arriving at the ground, having traveled many tens of kilometers. Why were these muons lasting so much longer than their lifetime suggested? The answer, physicists realized, lay in Einstein's special theory of relativity, and in particular, in a quantity known as the Lorentz factor, a measure that dictates the dilation of time. To explore this, we must understand one immediate and stunning consequence of special relativity. The speed of light is an absolute speed limit to the universe. No matter how hard we try, no matter how much energy we have available, no object with mass can ever reach the speed of light. The Lorentz factor depends on the relative velocity. As speeds get closer to that of light, the Lorentz factor grows unbounded. And so, though for the muon its life is over in just 2/millionths of a second, for the physicists here on Earth, the muon's life appears much longer, and it makes it to the ground. Of course, there is a flip side to this story, the other side of Einstein's strange relativistic coin. The physicists see the long-lived muon traveling tens of kilometers before decaying, but if you could ask the muon, it would say it had only covered a few hundred meters in its short life. Space, as well as time, can be distorted and dilated when speeds get close to that of light. Einstein also realized that this speed limit had profound implications for information. It too could not be transmitted faster than light. A classic example is that we don't see the sun as it is now but as it was 8 minutes ago. the light we see from the Andromeda Galaxy set off before humans walked the Earth. Through their telescopes, astronomers see galaxies as they were billions of years in the past. Indeed, the universe as it is now is completely hidden from us. We only spy it as it was, along what is known as our past light cone. The further away an object is, the younger it appears. Other consequences of Einstein's view began to flow. Where time and space mean different things to different observers, there is no universally agreed now. The relative nature of time means that observers disagree on how much time has passed. Einstein immediately realized that this doomed a cherished idea, the idea of synchronicity. This is the notion that two events, at two different locations, happen at exactly the same time. We experience this every day. It is part of the rhythm of life, where things seem to happen simultaneously. But this is all an illusion. To understand why, let's take a look at one of Einstein's thought experiments. The train experiment. Consider three people riding in a speeding train carriage. One person stands at the back of the carriage, one at the front, and one in the middle. As the train trundles along at uniform speed, these three people decide to perform an experiment. The person in the middle has equipment that will release a pulse of light. That pulse will travel simultaneously toward the back and front of the carriage. At each end of the carriage, a person has a mirror that reflects the pulse back towards the middle, and at the instant the light is reflected, they raise their hands. Of course, in any practical train carriage, this experiment would be over in a flash, and human reaction time would be the limiting factor. But this is the beauty of thought experiments. We can ignore such real-world limitations and focus purely on the physics. On the train, everything seems symmetrical. The light pulse heads outward, reflects, returns to the center, and the experiment ends. It seems perfectly reasonable to say that both hands were raised at the same time, that it was synchronous. But now, let's think about the view of an outside observer standing on the platform. And for fun, let's make the train move very fast, close to the speed of light. What does this observer see? Remember what Einstein's special relativity demands, that all observers see light travel at exactly the same speed, the speed of light. This has a curious influence. As the train moves, the back of the carriage moves toward the light pulse, reducing the distance the pulse has to travel. Meanwhile, the front of the carriage moves away, increasing the distance to the reflecting mirror. Eventually, both pulses bounce off their mirrors and return to the middle at the same instant. But when the outside observer is asked to describe what they saw, they will say, the pulses were emitted at the same time. The pulses returned to the middle at the same time. But the reflections and the hand raises happened at different times. Synchronicity depends on who is doing the observing. Einstein's next problem: gravity. While Einstein was pleased with the special theory of relativity, he immediately spotted a problem: gravity. Isaac Newton had given us his equations to describe gravity back in the 17th century, and they worked well to explain the fall of an apple or the orbit of the moon. But Newton's equations depended on the distance between masses, and in Newton's universe, where time is absolute, you can talk about a precise separation now. In Einstein's universe, where now is not universally defined, just which separation should we consider? This lack of synchronicity threw out the notion of a unique distance. Einstein could find no way to shoehorn Newton's gravity into his relativity. Eventually, he had no choice but to reject Newton's gravity entirely. He had to go back to the drawing board and redefine gravity from the ground up. Where, then, could gravity be included? The answer was even more bizarre than anything that had come before. Both time and space are malleable. Gravity could be encoded in the bending and stretching of the fabric of the cosmos. It took a decade of effort, but in 1915, Einstein cracked the mathematics. It is this general theory of relativity that we use today to describe the action of gravity. No longer is gravity a force between two masses. Now it is the curvature of spacetime itself. These mathematics describe the expanding universe and even power the technology that helps run GPS satellites. The conclusions of Einstein's relativity still hold across the cosmos. There is no synchronicity. No universally agreed now. Time and space can be immensely warped and distorted. Whether events happen at the same time is simply in the eye of the observer. Returning to the quasar study, 2023, And so we return to the remarkable quasar study from 2023. Did time really run slower when the universe was young? If you were there, back in the infant cosmos, 1 second would feel like 1 second. But as the universe expands, the light that travels through it is stretched. This stretchy, malleable nature of spacetime leads to what we observe in the distant cosmos, events pulled thin across time. It seems to us that the distant past ticked by at a slower pace. An even more extreme version of this concept appears around black holes. Spacetime is warped to impossible extremes at their centers, but even near their horizons, time slows down dramatically. Your experience of time slows down in comparison to distant observers. And bizarrely, these two ideas, time dilation in the early universe and time dilation near black holes, despite arising in vastly different contexts, are effectively the same phenomenon. Einstein's revolutionary view of time. From the earliest decades of the 20th century, our vision of time was changed forever. In Einstein's revolutionary universe, the passage of time is utterly personal. Your clock, mechanical or biological, ticks at a regular 1 second per second for you. But other people's clocks can tick radically differently if they are moving relative to you. They are located differently within a gravitational field. They are positioned in a different epoch of the life of the universe. This bending of time is simply part of the cosmos. The long-lived muons smashing into the Earth's surface are a testament to this, as are experiments where atomic clocks flown around the Earth return desynchronized. And we might even be able to use this relative nature of time to travel into the future. All we would need to do is hang out near a black hole, a place where time relative to the outside universe effectively grinds to a halt. While minutes or hours pass for you, years and decades could pass for those beyond the black hole's grasp. Back to the apple. Pulling yourself away from the distant universe, you drag your attention back to the apple. You feel sure that the apple is here, now, no more than a couple of meters away. But you now must accept that your now is precisely that. Your now, the now that belongs to you alone. Another way that your reality is yours, and yours alone. This thought makes you furrow your brow as the idea swirls in your mind. When and where reality is seems a slippery question. But what it is, perhaps that could be simpler. What is the world? Around you, what is the universe made of? How would you dismantle the universe? When the atom was split, a huge force was released, so screamed the headlines of the Melbourne Argus in May 1932, celebrating the Cambridge achievement, the success of British scientists. The nature of reality had been smashed into pieces. The headline was carried in a newspaper 0 kilometers from the laboratory in Cambridge, a testament to the earth-shattering nature of the discovery. A goal of ancient philosophers and seers had finally been achieved. The British scientists, Ernest Walton and John Cockcroft, were modern-day alchemists, but instead of fire and brimstone, their laboratory gleamed with metal and wires. With electricity, magnetism, and a beam of particles, they were able to transmute elements. Lithium was split into 2 new atoms of helium, their discovery showing that the world of the subatomic was now in the physicists' grasp. The question of just what matter is had been on the minds of philosophers for a long time. Some objects were clearly similar. Stones of various shapes and sizes were hard, while the solidness of stones contrasted with the squishiness of human flesh. They seemed quite different, even fundamentally different at their core. Philosophers wondered if the stuff of nature was infinitely divisible, whether, like our apple, you could continue to slice it and dice it into smaller and smaller pieces forever. But ancient Greek and Indian thinkers had a new thought, that things are composed of ultimate pieces, tiny indivisible units we now know as atoms from the Greek atomos, meaning uncuttable. To the ancient philosophers, these atoms were the fundamental pieces of reality. However, the notion that all things are made of atoms remained a philosophical musing for a few thousand years. By the 18th century, however, scientific evidence for the physical existence of atoms was emerging, and not from the experimental laboratories of physicists, but from that of a botanist. The botanist in question was Robert Brown, born in Scotland in 1773. He had a distinguished career traveling the world aboard the ship The Investigator, charting plant life. Many years later, in 1827, he was still studying the world of plants. His focus had turned to tiny grains of pollen floating on the surface of water. Brown examined them under a microscope, but what Brown saw mystified him. Instead of resting peacefully on the water, the pollen grains danced and jiggled. Brown knew that pollen came from plants, so perhaps the jiggling was due to life in action, some hidden propulsion within the pollen grains themselves. But when he examined clearly dead material, like chalk dust, he saw the same kind of dance. This Brownian motion had nothing to do with life. Many pondered the question of the jiggling pollen, but the answer would not be found for another 7 decades until 1905, arguably the most famous year in the history of science, Albert Einstein's Annus Mirabilis, his miraculous year. In this year of miracles, Einstein is generally remembered for one particular discovery, his special theory of relativity, and all the weirdness of space and time it revealed. But it is also the year he revolutionized quantum physics through the photoelectric effect and crucially explained the weird motion found by Robert Brown. Einstein's insight was as simple as it was brilliant. He realized that the jiggling of the pollen was not the pollen propelling itself, but being propelled by external forces, forces delivered by the collision of individual water molecules. But how could this possibly be? A pollen grain, while tiny, is a billion times heavier than a water molecule. How could the crash of a water molecule into pollen have any influence at all? Imagine you were at a truly massive rock concert, with music blasting from the stage. You were deep in the crowd, a crowd of tens of thousands of people. Now and again, the crowd surges to the left or right, front or back. In these surges, all you can do is go with the crowd. The surges die away, but the crowd remains restless. You are jostled from all sides, pushed from here, shoved from there. Your body moves as you try to hold your space, but you slowly start to jiggle about due to the relentless, unpredictable pushes. No matter what you do, you move a little this way, a little that way. Einstein realized that Brownian motion was precisely this kind of drunkard's walk. Every second, an uncountable number of water molecules collide with a pollen grain. The net result of these fluctuations and collisions leads to the random, perpetual jiggling, and the pollen grain dances to the molecular tune. From his calculations, Einstein was able to predict the size of the collisions and their fluctuations, confirming that water was made of an immense number of absolutely microscopic molecules. Thus, the atomic hypothesis became atomic reality, and atoms appeared to be the building blocks of our world. And yet, just as their existence was proven, these indivisible atoms began to divide. The splitting of the atom. In 1896, Henri Becquerel and Marie Curie found that the world of the atom was unstable, that some elements could transmute into others, spitting out pieces as they did so. In 1897, J.J. Thomson discovered the electron. It was clear that something was living inside the atom, something that made up reality. The race to split the atom and reveal its contents was on. For his discovery, Thomson was awarded a Nobel Prize in 1906, but it was his protege who would truly reveal the structure of matter, the father of nuclear physics, Ernest Rutherford. In the first decade of the 20th century, Rutherford set 2 young men to probe the structure of matter. In a dark room at the University of Manchester, they peered into inky blackness, looking for tiny flashes that indicated a collision, as tiny particles hit a fluorescent screen. Their results had been precisely as expected until Rutherford had a new idea. The 2 men, Hans Geiger and Ernest Marsden, Geiger's name would soon be immortalized in the Geiger counter, patiently stared into the darkness, logging each of the tiny flashes they saw. The experiments continued, flash after flash, until Rutherford suggested they look for flashes where none should be. And it was then they changed our understanding of physical reality forever. Rutherford was stunned, later saying it was the most incredible event of his life. At 40 years old, he was still quite young, but had already won a Nobel Prize. This new discovery, however, would redefine science. But what had they seen? And what did it mean? The plum pudding and the unexpected truth. Thomson's discovery of the electron had provided a new clue to the structure of atoms. The electron clearly carried negative electric charge. Therefore, atoms must be a mix of positive and negative charges because overall they are neutral. The question was how this charge was distributed. Thomson proposed the plum pudding model of the atom, a positive pudding embedded with negative raisins, electrons. It was precisely this model Rutherford was testing. He created a beam of alpha particles, charged helium nuclei emitted from a radioactive source, and directed them at a thin gold foil. Geiger and Marsden watched the collisions in the dark. If Thomson's model were correct, the positive charge was spread throughout the atom, and the alpha particles would only be gently deflected as they passed through. Indeed, most of the alpha particles sailed right through the gold foil without any deflection at all. But every now and again, something astonishing happened. Some alpha particles were scattered at enormous angles, even bouncing almost straight back. Rutherford was astonished. He later said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Such massive deflections were impossible if Thomson's plum pudding model were correct. Atom could not explain the scattering of alpha particles. What Rutherford concluded was that, instead of being spread out, the positive charge must be tightly concentrated so that there is an immense electromagnetic repulsion between the atomic charge and the alpha particle. So immense, in fact, that the alpha particle can be flung in any direction. This led to a rather confounding picture of just what an atom is. Rutherford knew that the electrons in the atom carried a negative charge. This charge must be broadly spread over the volume of the atom, spread so thinly that they barely influence the alpha particles. The electrons, however, carried very little mass. This meant that the totality of the mass must sit in the positive charge at the nucleus of the atom. But whilst massive, the nucleus is very small, tens of thousands of times smaller than the atom. And so, with this, the vast majority of the volume of an atom became nothing but empty space. With Rutherford's insights, the startling Pandora's box of nuclear physics was open. Rutherford's atom fractures our view of reality of the apparently solid nature of the world around you. Every chair, every wall, every tree, every apple is made of atoms tied together into myriad molecules that define structure, color, and everything else. But it seems that this is nothing more than an illusion. Apples are made of water, vitamins, and butyl and hexyl acetate, the molecules responsible for their taste. But each atom in each molecule is really a cloud of electrons surrounding a minuscule nucleus, and the vast majority of each atom is nothing but empty space. So the apple is mostly empty space, and its solid appearance but an illusion. Of course, it's not only the apple, but everything that has the illusion of being solid, everything, including yourself. This is disconcerting, but maybe you can try and comfort yourself with this image of yourself in reality. Maybe it's okay that atoms are mostly nothing but empty space. They're still made of something with a nucleus and orbiting electrons. Surely those pieces are real. Surely those pieces are really there. But as they had with the molecule and atom before it, physicists would quickly realize that the mysterious nucleus of an atom was also far from fundamental. On the 10th of August in 1915, a sniper found his target. His rifle trained on the enemy, he steadied his breathing and began to apply gentle pressure to the trigger. Birds scattered as the shot rang out. The sniper's aim was true, and the enemy crumpled to the ground. The sniper moved on, there were plenty more to hunt. But little did he know that his bullet had snuffed out one of the greatest minds of the 20th century. World War I cost 20 million lives, both soldier and civilian, with many more wounded and injured. The failed Gallipoli campaign, seeking to weaken the Ottoman Empire, cost 100-0. Every life lost is a tragedia, missing loved one whose potential goes unrealized. But this is particularly true of Henry G.J. Moseley. For before he joined up to be a soldier, something he did out of duty and against the wishes of his family, Moseley was a scientist who was unraveling the inner workings of the atom's nucleus. Born in 1887 in Dorset, England, the son of an Oxford professor, Moseley was a stellar student, studying at Oxford before joining Rutherford in Manchester in 1910. He had started to use X-rays to bombard different elements with the hope of revealing the secrets of their atoms. As he did this, he had spied X-rays being emitted at different energies, and guessed something deep within the atom was causing them. There was also a pattern. In heavier elements thought to contain heavier atom-shire energy, X-rays were emitted. In Holland, the amateur physicist Antonius Johannes van den Broek presented a bold idea. He knew that electrons carrying the negative charge inside atoms came in discrete chunks. Each electron appeared to have the same mass and the same charge. So, what if the nucleus was the same built of separate but positive charges? All atoms appear to be electrically neutral. So, these positively charged chunks should exactly balance the negatively charged ones. And the only difference between the elements would be the number of positive charges in the nucleus, as this would set the number of orbiting electrons and dictate how the atom interacts with others. The simplest element would have one of these charges, the next two, and so on. And Moseley realized that this was the pattern he was seeing with his X-rays. With this one insight, he rearranged the periodic table based on what we now know as the atomic number still, the form of the periodic table that we use today. Speaking in 1962, long after Moseley's untimely death, the giant of quantum mechanics, Niels Bohr, said, "You see, actually, the Rutherford work was not taken seriously. There was no mention of it in any place. The great change came from Moseley. And who knows what else Moseley would have contributed to science had he not been cut down by that sniper's bullet in 1915. Things moved quickly as the Great War ground towards its eventual end. It was again Rutherford always at the forefront who was deep in the discovery. Through his investigations into radioactivity, he finally uncovered the true nature of the atom. Hydrogen was the simplest element, just one piece of positive charge joined by one electron, whereas helium had two positive charges and two electrons. Then lithium with 3 of each, beryllium with 4, and so on and so on. Like the electron, each of these positive charges were identical both in terms of the charge they carried and the mass they were made of. Rutherford named these positively charged massive particles protons, and eventually, in 1932, after being theorized for years, the neutron was also identified in experiments. The makeup of the atom was complete. It had started off as a mess of complexity, becoming simplified through the realization that the world is built from 92 natural elements. But with the discovery of the proton, neutron, and electron, things became simpler still with atoms of all the elements and their isotopes built of nothing but these 3 key pieces of reality. In the outer reaches of the atom roam the electrons' negatively charged tiny particles that whiz around at close to the speed of light. And at the very heart of the atom sits the nucleus positively charged and comprised of protons and neutrons. It is the home to atomic mass. But as Rutherford's new view of atoms took hold, others realized it spelled doom for physics as they knew it. It contained a fatal flaw. There is, they said, no way an electron can remain in its orbit. Rutherford's version of the atom should not be able to exist at all. The problem came from James Clerk Maxwell's equations of electromagnetism. These demanded that an accelerating charge must radiate away its energy as electromagnetic waves. And as an orbiting electron is in a constant state of acceleration, it must constantly lose energy. It should spiral into oblivion in the nucleus of the atom. There was nothing in the physical laws of Newton or Maxwell that seemed to prevent this. Nothing in the laws of reality, as we understood them, could make matter stable. So physicists made a decision. They decided to change the rules and in the process, change the nature of reality forever. In 1943, the father of quantum mechanics, Niels Bohr, found himself in a predicament. Germany had declared his family Jewish, and his arrest was imminent. So, with the help of the Dutch resistance, he fled to neutral Sweden. But his trials and tribulations were not over, for the British heard of his escape and decided they needed this quantum legend. The Second World War had been raging for 4 long years, and the Allies had decided that a new weapon, an atomic weapon, must be developed to end the carnage. Bohr's insights into the subatomic world would benefit them and stop the enemy from following the same path. Retrieved from Sweden and traveling in disguise as James Baker, Bohr eventually made his way to a secret town in New Mexico. And there, at Los Alamos, he contributed to the Manhattan Project and the building of the atomic bomb. Still, he always claimed that he wasn't really needed amongst the bright young minds, but project director Robert Oppenheimer disagreed. The early days of quantum mechanics were a heroic time. It was not the doing of any one man. It involved the collaboration of scores of scientists from many different lands. But from the first to the last, the deeply creative, subtle, and critical spirit of Niels Bohr guided, restrained, deepened, and finally transmuted the enterprise. For 3 decades earlier, in 1913, the world had been on the precipice of another world. Bohr's mind had been focused not on how to unleash the power of the atom, but on the question of why atoms existed at all. If Rutherford was right on the structure of the atom, then why didn't the electron simply spiral into the nucleus, just as the physical laws of Newton and Maxwell predicted? A demanded revolution had been brewing. By the close of the 19th century, physics had seemed pretty complete, except for a few niggles. Yet those niggles came to dominate and rewrite physics as we know it. And it all began with the question of why hot objects glow. Clearly, to make an object glow, you have to supply it with energy. This energy makes atoms vibrate vibrations that generate light. We know that an iron poker in a fire glows with a beautiful cherry red, and as we make it hotter, this red gives way to white and then to blue. But the question of why this particular choice of colors became the focus of a 42-year-old Max Planck, who combined the rules of established physics to understand how matter and light interacted. His calculations failed, time and time again. And as he reached a moment of absolute despair, he decided to rewrite the physics rulebook as many had done before him, and would do after, but never again with quite such far-reaching ramifications. Electromagnetic energy, he said, came in distinct packets of light. These discrete vibrations-like package had to be quantized. And suddenly, Planck's strange new mathematics explained the glow of a hot poker. Planck thought all he had done was perform a little mathematical wizardry. But by 1905, Einstein also said that light comes in discrete chunks quanta of energy, explaining how electrons are ejected from metal when under a light source. Suddenly, the quantized world was popping up everywhere. The quantum revolution was gathering pace, as the subatomic world was laid bare. And it was Rutherford's insights that showed the atom itself would have to be quantized. But just what rules governed this quantized atom eluded him. The answers came from Bohr. Electrons, said Bohr, were only allowed to exist in distinct orbits around the nucleus. These orbits were set by the momentum of the electron, and so each orbit had a specific energy. Electrons could move between orbits only if the exact energy difference was absorbed or emitted. And there would be a smallest orbit that brought the electron no closer to the nucleus. In demanding electrons could only exist in certain orbits with certain energies, Bohr had quantized and saved the atom from collapsing in on itself. With only chunks of energy able to change the atomic state, this was a resounding success for Bohr, securing him the Nobel Prize in Physics in 1922. But physicists still scratched their heads as to why the atom was quantized. That answer would come 2 years after Bohr received his prize in Sweden from a radical proposition by a French aristocrat and physicist named Louis de Broglie. He had been watching the quantum revolution unfold and was perplexed by the notion that light, which was a wave in classical electromagnetism, sometimes behaved like a particle, delivering its energy in a single punch. In this quantum world, thought de Broglie, why should matter not be subject to this duality? So he declared that an electron, which had been thought of as a distinct particle, also possessed wave-like properties. Just like light, de Broglie said, electrons can be refracted, and they can interfere. And it was Schrödinger who applied this to Bohr's atom, asking us to think of the wave of the electron as not at a precise point, but spread over the entirety of the orbit. And so Bohr's quantized atom finally made sense. The electrons were behaving as waves, and could only have certain wavelengths. Today, the notion that quantum objects can be particles and waves is common knowledge, but in its time, de Broglie's ideas shook the foundation of physics to its core. And in 1929, de Broglie found himself in Sweden, receiving his own Nobel Prize. By the 1930s, it seemed that reality was all sewn up. The periodic table was built of just 3 particles, protons, neutrons, and electrons, bound together in different ways by the mathematical rules of electromagnetism and quantum mechanics. But even this neat picture rapidly started to unravel. In 1929, English physicist Paul Dirac had been focused on the equations of quantum mechanics. His goal was to make quantum theory consistent with the other great physics theory, Einstein's relativity. His new equations worked, but immediately Dirac was puzzled by what they told him. For as well as describing the behavior of electrons, something else was in the mathematics. The equations also described a positively charged electron-positron, a particle that seemed to have no place in the orderly atomic world. Perhaps, people thought, it was nothing more than a mathematical oddity that had no place in reality. But by 1932, it was unmistakably found in particle experiments. Soon after the discovery of the positron, a much stranger particle appeared in the collision zone that had even less of a place in the atomic world than the positron. It looked like an electron, with the same electric charge, except for one key difference. This new particle appeared to be 200 times as massive as the electron. And unlike the electron, this new particle, the muon, decayed in 2/millionths of a second. So the big question was, why does the muon exist, when it seems that it's not needed to build reality? Indeed, particle physicist Isidore Rabi quipped, "Who ordered that?" as the muon made a mess of atomic neatness. But its discovery was the start of a cascade, with many strange and differing particles popping out of experiments. And so, into the 1960s, chaos reigned in the world of the subatomic until the next level of reality was bared. In what became known as the Standard Model, it was realized that protons and neutrons and most other particles are not truly fundamental, but are made of even smaller pieces known as quarks. We now know that there are 6 kinds of quarks, grouped into 3 families. The lowest mass, up and down, then charm and strange, most massive, top and bottom. The vast array of particles spat out in experiments are combinations of these quarks. Protons and neutrons are built from up and down quarks. Protons are 2 ups and a down, while neutrons are 2 downs and an up. 3 up quarks combine to form a delta Joule particle, whereas a d Joule is a charm quark combined with an anti-down quark. As well as the quarks, there are also the leptons, the electron, the muon, and the even more massive tau, plus their ghostly companions known as neutrinosone for each kind of lepton. The majority of reality we experience is a combination of electrons and up and down quarks. There are a few other pieces to the Standard Model, and we'll meet those soon, but it's important to note that these fundamental pieces appear to have no size at all. These truly fundamental pieces of reality are point-like. So, in a way, each of your protons and neutrons is effectively empty at the subatomic scale. Your atoms are even emptier than Rutherford found. Your brow furrows as you think again about the apple, knowing that it is mostly empty space, was disturbing enough, but at least the electron and the atomic nucleus seem solid. In the quantum world, this is simply not the case. Everything we thought was a particleized knot. Quantum matter shows wave-like properties, spread out over space and not in any precise location, or with precise properties. Your apple is nothing more than a mix of these bizarre waves, all combining to be the fruit you see. You squint at the apple, as the question of quantum waves washes over your mind. Just what are these waves? And just what is doing the waving? Is this what reality is, just a sea of subatomic waves? A strange analogy. Imagine that you are in your kitchen mixing ingredients to bake a cake. As you read through the recipe, you see that you need a couple of eggs, so you head for the fridge. In the fridge door, the eggs are neatly arranged in lines, with some holes filled and some holes empty. You close the door and get back to your baking, thinking little of the remaining eggs. In your mind, there are certainties. When you open the fridge again, the eggs will still be there, occupying the same holes as before. How could it be any other way? But our modern understanding of reality suggests that the universe is actually much stranger. Instead of eggs, let's think of a collection of electrons, similarly arranged in holes. With the arrival of quantum mechanics in the early 20th century, it was realized that electrons cannot be described by the rigid rules of Newtonian physics. Instead of exact positions and velocities, electrons were described by probabilities. Mechanics and so by probabilities. Well, in a sense, they do. For although the chance of an entire egg quantumly jumping between holes is extremely tiny, it is not zero. Though very unlikely, within the laws of physics, everything is possible in the quantum world. It is just a case of probability. The quantum revolution dominated the physics of the early 20th century. Great minds from around the globe turned their attention to the strange realm of the subatomic. But not everyone was pleased with what this revolution had to say, including perhaps the greatest scientist of them all, Albert Einstein. The problem started in 1926, in a paper by the physicist Max Born. A year earlier, Erwin Schrödinger had published his now famous equation. This allowed physicists to calculate the properties of de Broglie's matter waves. But Schrödinger still didn't know just what these waves were. Born, however, said that everything makes sense if you interpret the waves as waves of probability. The amplitude of this wave function, he said, tells you the chances of an electron being here or there. And as time ticks by, this wave function can wash back and forth, as the probabilities for an electron being in a particular location change. This answered one of the questions that had been nagging physicists when considering quantum waves, because when they experimented on electrons, they would see precise dings in their equipment. They would detect individual electrons as distinct particles, so how could they also exist as quantum waves? To Born, the answer was clear. Particles like electrons behave like waves as they travel from one place to another. But when they interact with your detector, the wave collapses, and the electron is at a precise spot. Experimental evidence was quickly sought to see if this picture was correct, and it didn't take long to arrive. The experimental setup was similar to Young's famous double-slit experiment, where light was shown through two slits and produced unmistakable patterns of interference. This demonstrated that light traveled as a wave, as you need waves to create interference patterns. And if quantum matter behaved like waves, it should show interference too. The idea was to fire a beam of electrons onto a target of nickel with a regular pattern of atoms. If the electrons were little bullets, we would expect them to randomly ricochet off the target atoms. However, the experimenters found that there were certain directions in which electrons preferred to recoil and other directions they seemed to avoid. This was the unmistakable pattern of interference, places where waves added and strengthened, and others where waves cancelled each other out. To help understand this, imagine you're a sharpshooter at the Olympics. Through your sights, you zero in on your target, 100 meters away. You line up your crosshairs, take a deep breath, and hold it. But as you think about your glory yet to come, your mind starts wandering. What if you were a sharpshooter in the quantum world? In the quantum world, the certainty of everyday physics melts away. Instead of exact location and velocity, your bullet is now governed by the rules of quantum probability. When you squeeze the trigger, the bullet emerges from the barrel not as a single object, but as a quantum wave, spreading out in all directions like ripples on the surface of a pond. This quantum wave travels quite differently from the zipping path of a classical bullet. Quantum waves can diffract around corners and can interfere with other quantum waves. Indeed, a spray of quantum bullets would not result in a neat grouping of holes in the target. Instead, an interference pattern would emerge with some bullets here and none there. This strange mix of wave-like and particle-like properties in the quantum world is known as duality. And quite why we don't experience this in everyday life remains a mystery, although physicists have been able to see the effect of quantum waves even on the scale of large molecules, many tens of atoms traveling together as a quantum wave and showing interference. And so, experiments showed precisely as Born had suggested. The waves of the electrons were combining and cancelling, but bizarrely, their detectors were counting just individual electrons arriving. Quantum objects were definitively traveling as waves, but interacting with detectors as particles. Indeed, as further proof, today we use this fact in our most powerful microscopes. Instead of a beam of light, these microscopes focus a beam of electrons onto a target and use the wave properties of the beam to reveal details beyond what is visible to light. Born received his Nobel Prize in 1954, 1 year before Einstein's death. But in the decades in between, Einstein had become a vocal critic of this probabilistic picture of nature, convinced as he was that it could not be the way the universe actually worked. Einstein and Born were friends, but they never saw eye to eye on reality. Einstein was horrified by the idea of probability sitting at the heart of our world. He felt that the universe must be deterministic at its core. Though he accepted that quantum mechanics could be probabilistic, he believed there was something deeper, something hidden beneath the quantum world that still clung to determinism. Indeed, in a now iconic letter to Born, Einstein wrote, "I, at any rate, am convinced that God does not play at dice." By 1935, Einstein had fled Nazi Germany and arrived in the USA. It was there he wrote about a paradox at the heart of quantum mechanics, a paradox he was convinced would demonstrate the absurdity of some of its big ideas. This paradox, almost a century old, is still key to our modern understanding of the quantum world. It is known as the EPR paradox, after its authors, Einstein, Podolsky, and Rosen. And it highlighted one of Einstein's biggest problems with quantum mechanics, the apparently instantaneous collapse of the probability wave into a particle upon observation. To understand its impact, let's start with two quantum particles. One of the interesting things about the wave function is that when we have two particles, the wave function for both is not simply the sum of the individual wave functions. No, a new wave function can be written, one that encapsulates the properties of both particles. And it's this combined wave function that gave Einstein a headache. Imagine the two particles are created in some shared event. The details don't matter. What matters is that they are created with linked quantum properties. For example, imagine the particles are born with quantum spin, one spinning up, one spinning down. This way, the total spin is zero, so spin has been conserved. Except, the wave function does not contain definite information, just probabilities. Each particle has a 50% chance of being spin up and 50% chance of spin down. However, because total spin is conserved, if you detect one spinning up, the other must definitely be spinning down. In Einstein's thought experiment, you can imagine these particles separating after their creation, moving an immense distance apart, maybe several light years. They travel as probability waves. You don't know the spin orientation of either. Everything is still a mix of probabilities. This is quantum entanglement. But imagine one particle runs into a spin detector. Beep. It registers spin up. Now you instantly know the other particle is spin down. The wave function has collapsed into definite, separate states. But here's the issue. How does that other particle light years away know that its twin has had its spin measured? Did the wave function collapse instantaneously, possibly across light years? If so, then the wave collapse would occur faster than the speed of light. And that, Einstein said, is forbidden. Nothing can travel faster than light. His conclusion? Quantum mechanics must be incomplete. Beneath its probabilistic surface, Einstein believed, lurked something more, hidden variables, deterministic values that precisely described reality. We simply hadn't found them yet. The hunt for these hidden variables was on. Einstein and de Broglie put forward new ideas, then threw them away. Others sought answers to the EPR paradox, hoping to restore determinism to the heart of physics. But by the 1960s, all such attempts were dashed by the insights of an Irish physicist in Switzerland. John Stuart Bell, born in Belfast in 1928. From a young age, he had decided he wanted to be a scientist. And in 1960, he found himself as a theoretical physicist working on the Swiss-French border at the recently formed European Organization for Nuclear Research, CERN, for short. Bell contributed many things to physics and the understanding of reality, but he is probably best remembered for what is known as the Bell inequalities. His thought experiment was similar to that laid out in the EPR paradox, but with a subtle and insightful twist. Just like in the EPR paradox, we first make a pair of particles that are entangled in their wave function. Then we allow them to separate over a large distance, where each encounters a detector. The detectors can register spin up or spin down, but each can be oriented differently. Let's start by imagining that the two detectors are perfectly aligned. As we've seen before, if one detector registers an up, the other must register a down. So, if the readings on one detector are up, up, down, up, down, 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 the other must read down, down, up, down, up, up, up. The readings are perfectly correlated. Bell's twist was to consider what would happen if the two detectors were not aligned. What if one was set to register up, down, and the other was twisted to measure left, right? This might sound strange after all. If a particle is spinning either up or down, how could it register any spin left or right? But if you're thinking like this, you're still imagining the particles as classical objects, as if they are solid balls with a definite direction of spin. They are not. They are purely quantum particles, and their spins are probabilistic. So, there will be some probability of spin up, down, and some probability of spin left, right. Though thinking like this can bring on a headache, it is how the microscopic world works. Bell began to wonder about the correlations of the outputs, say, one detector reading up, down, 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 up, up, and the other reading right, 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 left, left, right. He concluded that if the choices of spin were being made by hidden variables definite, deterministic quantities tied to each particle, then a particular pattern of correlations should be observed. But if there were no hidden variables and the photon's properties were spread across the quantum wave function, then a different pattern would emerge. And so, the rush to test Bell's experiment was underway. It wasn't long before the first results were on the table. Calcium atoms were excited in a hot oven, emitting two correlated photons as they cooled. These photons zipped out of the oven and into physicists' detectors, which measured the polarizations of the photons, the direction in which their electric field vibrated. Bell said that if there were hidden variables defining the photons, specific correlations would be measured. But if there were no TAND, if their properties were spread out across the quantum wave function, then a distinctly different set of correlations would be measured. The results were conclusive. There could be no hidden variables. Reality was not a property of things, it was non-local, extended across the quantum wave. As many experiments since have confirmed, Einstein's notion of a deterministic underlying universe was quietly put to rest. At this point, you might be wondering, what does all this mean? Isn't this just an academic argument about exotic quantum stuff in weird experiments? But the ramifications for reality are huge. Locality has always been a key concept in physics. It means that something responds purely to its local environment. Proximity matters. A mass responds directly to a force acting upon it, doesn't know or care about a force acting on a distant mass. Indeed, it was this non-local nature of quantum mechanics that Einstein so strongly objected to. The idea that detecting a particle here can instantaneously influence another over there. In a 1947 letter to Max Born, Einstein famously referred to this as "spookhafte Fernwirkung," spooky action at a distance. And that was a step too far for his view of the universe. Because what this suggests when truly taken to heart is baffling. An electron is not simply an electron. Neither is any other fundamental particle in the universe. Particles are entangled with other sharing experiences across the cosmos. No individual thing is just a thing. Everything, universe-wide, is truly connected. At this point, you might be sharing Einstein's skepticism. There's no way, you think, my apple is entangled with particles across the cosmos. But we have to remember something fundamental. The universe simply doesn't care about your feelings. It doesn't care about your intuition, or what makes sense to your brain. It refuses to behave in the way we expect. And the awarding of the 2022 Nobel Prize in Physics only drove that point home. The laureates were Alan Aspect, John Clauser, and Anton Zeilinger. Their work focused on entangled photons. Over decades, these physicists showed that widely separated particles behave as one. Their goal was to dismiss any possibility of hidden variables defining reality. One of the most extreme examples was the cosmic Bell test. There was a new worry among physicists. What if their experiments themselves were compromised? After all, experiments are built of atom sand. Atoms have histories. What if, over billions of years, the particles making up the detectors had interacted in ways that could mimic quantum effects? Worse still, what if the experimenters themselves were made of entangled particles too? Physicists like to think of themselves as objective observers, separate from the experiment. They imagine their equipment as isolated from the rest of the universe, but that's not quite the case. The apparatus is made of atoms. Atoms that are billions of years old. Atoms that have had countless opportunities to entangle, to tangle, and to store history. This raised the possibility that the measured correlations could be due to this shared history, rather than any real non-locality. To close this loophole, physicists turned to the cosmos. They set up their experiments as usual, but added a twist. They used the light from distant stars billions of light-years away. These tiny fluctuations in starlight were used to randomly set the orientations of the spin detectors. And once again, the experiment revealed reality must be non-local. Even more remarkably, these experiments were repeated using quasars, the extremely bright ancient galaxies whose light has traveled nearly 8 billion years to reach Earth. Again, the particle spins were measured using settings determined by this ancient light. Again, the results were unequivocal. Reality is not simply there, it is entangled and spread out. You look again at your apple. It feels solid, there, whole, and you can handle the idea that it's made of fundamental particles. That feels sensible. But those particles? They are entangled not only with each other, but with others scattered across the universe. Your apple is spookily entwined with the cosmos. And now, the question becomes, why? Why exactly is this this universe so deeply, strangely, mathematically connected? On the 18th of April, 1955, the old man died. He had been born in Germany nearly 8 decades earlier, but his last moments were spent in an American hospital. His final words were spoken in German, but they are lost to us, as the nurse at his side did not speak the language. In his final hours, he had asked for 3 things: his glasses, his writing tools, and his equations, to work on one last problem. This man, Albert Einstein, is considered one of the greatest physicists of all time. His name is splashed across the pages of every physics textbook. But in the final years of his life, his focus narrowed to a single question, a question that still haunts physicists today. 2 central theories had emerged from the revolution of the early 20th century. We've met them both in our stories so far. Einstein's relativity describing the action of gravity across the cosmos. Quantum mechanics explaining the strange behavior of the subatomic world. The universe of the subatomic world, described by quantum mechanics, was refined throughout the 20th century, evolving into what we now call quantum field theory. It is in these fields that the rippling waves of probability in quantum mechanics live, and it is these fields that describe the physics of the fundamental pieces of reality, like electrons and quarks. We've already encountered the standard model of particle physics, and this is really a theory about the interaction of these quantum fields. When 2 charged particles, like electrons, interact, they create vibrations in the electromagnetic field. These vibrations carriers of the electromagnetic force are known as photons. And the electrons themselves? They are also vibrations in the electron field, just as each type of quark that makes up protons and neutrons is a vibration in its own quark field. And so on for other particles. There are also other fields for other fundamental forces. The strong force, which holds quarks together in protons and neutron sand, binds those particles inside atomic nuclei, mediated by vibrations in the strong field. These are the gluons. Then there's the weak force, responsible for certain types of radioactivity. Vibrations in the weak field correspond to the W and Z bosons. For every force, there is a field. And for every field, there are vibrations. And those vibrations, they are quantum particles. To understand this more deeply, let's take a look at the life of a neutron. Left on its own, a free neutron will decay in about 15 minutes, transforming into a proton, while spitting out an electron and a ghostly neutrino. But what's really happening here in terms of quantum fields? First, we remember that a neutron is made of 3 quarks, 2 down quarks and 1 up quark. These quarks are constantly generating vibrations in the strong field, with gluons flying around to bind the neutron together. But the weak field is still present too. Eventually, one of the down quarks interacts with that weak field, creating a new vibration. That vibration causes the down quark to transform into an up quark, turning the neutron into a proton. The ripple in the weak field? That's a W-Menes boson, which flies away from the newly formed proton. But this particle is incredibly unstable. It lives for less than a billionth of a second before its vibration disappears, creating vibrations in other fields, instead those of the electron and neutrino. And all quantum particle interactions can be described this way, as fields vibrating into other fields. But one more quantum field is needed to complete the picture. Perhaps the most famous of all, the Higgs field. Interactions with the Higgs field give mass to the fundamental particles. Its vibrations represent the Higgs boson, discovered in 2012 after a 4-decade search. In the early 1960s, physicists realized there was a serious problem. As we know, the weak force has two force-carrying particles, the W and Z bosons. But quantum field theory says that force particles must be massless. This works for photons, electromagnetic force, and gluons, strong force. Both are massless. But the W and Z aren't. Simply adding mass to them in the equations caused the math to explode into infinities. A new mechanism was needed, and that mechanism came from the Higgs field of energy that permeates all of space. The W and Z particles field this field. They couple to it. They gain mass through quantum interaction. The photon and gluon, meanwhile, pass through the Higgs field unaffected. The problem of their mass was solved. But physicists soon realized the Higgs mechanism could do more. It could give mass to all fundamental particles, all electrons and quarks. As these particles travel through the seeming emptiness of space, the presence of the Higgs field ensures they acquire just the right mass. It's not the emptiness that gives them substance, it's the field that fills the vacuum. Quantum field theory is incredibly successful. It accurately predicts what gets spat out of particle experiments, electrons, quarks, sprays of gluons, and more. And Einstein's relativity is equally successful predicting the motion of planets, the bending of light, the stretch of time. But ironically, it's this very accuracy that caused Einstein such distress. Even without knowing the modern details of the fundamental forces, he recognized the problem. The two great theories, the two great languages, were totally incompatible. Relativity describes gravity as the curving of space-time. Quantum mechanics describes matter as probability and waves. Two languages. Two visions of reality. You might wonder, why does this matter? Why can't we just use both when needed? But for physicists especially, Einstein, this division shattered the dream of modern physics, the dream of unification. That dream had its spark in the 19th century with James Clerk Maxwell. Maxwell's equations united electricity and magnetismons, thought to be separate forces. He showed they were simply different aspects of a single electromagnetic field. With the rise of quantum field theory, things seemed to unify further. Electromagnetism, the strong force, and the weak force could all be described in one elegant framework. One mathematical formalism, 3 of the 4 forces. It worked. Except for gravity. Gravity refused to fit. Soon after general relativity appeared, physicists asked, could extra dimensions help? What if spacetime had more than just 3 spatial dimensions? What if curled-up dimensions could hide the electromagnetic force? At first, the idea seemed promising, but it left a massive question. Where are these extra dimensions? Surely we'd notice if there were more than just up-down, left-right, and forward-back. Physicists proposed a clever workaround. What if the extra dimensions are curled up so tightly that we simply can't detect them? Like trying to do surgery with boxing gloves on, we simply lack the precision to probe them. Some even imagined many of these curled-up dimensions building blocks of a more complex reality. These ideas lay dormant for decades. But in the 1960s, they were reborn. Physicists realized that these extra dimensions could explain all the forces if they treated fundamental particles not as points, but as tiny loops of string. Thus began the string theory revolution. Through the 1980s and 90s, it looked like we were on the brink. Any day now, someone might crack the math and unveil the theory of everything. But The deeper they went into more than 20 dimensions, the more elusive unification became. Eventually, string theory evolved into M theory. M for mystery, or membrane, or simply magic, as some joked. Strings became membranes. Ideas shifted, but the final theory, still unrevealed. Not everyone bought into string theory. Others turned toward alternatives like loop quantum gravity. This theory attempts to knit spacetime itself from quantum chunks, imagining that space and time aren't continuous, but granular. But again, the mathematics has been daunting. No theory is one. Still, physicists persist. New frameworks are proposed, tested, and often rejected. And in this long search, physicists lean on one of the deepest concepts in all of science, perhaps the closest thing we have to a rule of the universe: symmetry. We all have a basic sense of symmetry: buildings, faces, or vases that look balanced and beautiful. But in physics, symmetry becomes a mathematical Tula principle of immense power. As Emmy Noether showed in 1915, every symmetry implies a conservation law. But what does that mean? Imagine you're doing a physics experiment trolling balls down a ramp. Now suppose you move your experiment 1 meter to the left and do it again. You'd expect the outcome to be the same. This shift in space didn't change the physics. That's a symmetry. And what's the conserved quantity? The mathematics of Noether tells us that the conserved thing is momentum. This property of motion mass times velocity in Newton's theory is conserved because of this symmetry. Momentum cannot simply disappear in a physical interaction, simply vanish. One billiard ball transfers its energy to another. Other symmetries exist and imply other conservation laws. If you rotate your experiment by 90°4 and repeat the rolling of the balls again, you expect the same outcome of your experiments. Now, the conserved quantity is angular momentum, the conservation of spin in the universe. But perhaps the strangest symmetry is that associated with time. The fact that if you perform your experiment today and then tomorrow, you expect the same results. This time symmetry results in what seems like one of the most fundamental rules about the universe. This time symmetry implies the conservation of energy. Energy itself cannot be lost or created. Symmetries run deep through our ideas of theoretical physics. Einstein's special relativity is built entirely on symmetries, and it can be derived from what is known as the Lorentz group of symmetries. Indeed, it is these symmetries that demand that the speed of light is the fastest speed there is. But it is in quantum mechanics that symmetries truly reign supreme. It was realized that electromagnetism contained a symmetry, unexcitingly known as U(1), and that other symmetry groups, with more esoteric names, described the strong and weak forces. With these symmetry groups came new conserved quantities. For electromagnetism, the quantity that is conserved is charge. But for the other forces, other quantum numbers appear quantities that seem quite unfamiliar. Things like isospin, lepton number, quark numbers, and a host of others. These all represent the rulebook of reality, defining what can and cannot happen. If the conservation laws hold, then interactions can occur. But if they are broken, interactions are strictly forbidden. Deep, deep down, reality appears to be built on symmetries. And so, in the search for even deeper reality, physicists have tried to incorporate more and more symmetries. With supersymmetry, physicists try to hold a mirror up to the Standard Model, reflecting all existing fundamental particles with supersymmetric counterparts. So, for electrons, there should also be selectrons. For photons, there should be photinos, and so on. Supersymmetry improves the mathematical elegance of the Standard Model, and, for some, indicates the true path to enlightenment. But there has been no sign yet of any of the supersymmetric particles in any experiment. This, many claim, shows that supersymmetry as an idea is dead. Groups of symmetries also sit at the heart of string theories and M theories, and different symmetries are used to clean up and clarify loop quantum gravity. And so, clues keep coming from geometry and symmetry, with many putting their faith in what is called the anti-de Sitter conformal field theory correspondence. This mouthful, usually abbreviated as ADS-CFT, was found by Argentinian Juan Maldacena in the late 90s, a mathematical mapping between aspects of string theory containing gravity and particle theories. It showed that the mathematics of one particular four-dimensional universe without gravity, a universe built on quantum mechanics alone, could match that of a five-dimensional universe with gravity. In short, there was a clear mathematical link between the two, gravity and quantum mechanics. Immense effort has been placed in uncovering whether this correspondence tells us something deeper, perhaps a shadow of the true theory of everything that rules reality. However, the ADS, CFT correspondence could also have very bizarre implications. You might be familiar with the notion of an optical hologram, where a three-dimensional image is encoded in a two-dimensional space. One of the possible consequences of the ADS, CFT correspondence is that this may be the case for reality. What we experience as reality could really just be a projection of information stored in lower dimensions. And just like an optical hologram, nothing but an illusion conjured up from a two-dimensional plane. This notion, known as the holographic principle, grew out of our understanding of black holes. Black holes are extremely simple objects, completely described by only their mass, angular momentum, and charge. A black hole carries no memory of the objects that have ever fallen in. All information other than those three properties is seemingly forgotten. But in physics, it is generally accepted that information cannot be created or destroyed, only processed from one form to another. So, for black holes, the question of just where all their information goes was problematic. Originally, it was suggested that the information is still there, encased in the black hole's heart. Here it would just be hidden from the rest of the universe, out of sight and out of mind. But in the early 1970s, this picture was completely demolished, destroyed by the insights of a young physicist named Stephen Hawking. Hawking had wondered about the impact of quantum mechanics near a black hole. He eventually showed that the supposedly one-way influence of the event horizon, which allows things in but nothing out, conjured particles out of the foaming quantum background. These particles escaped into the universe, carrying energy with them. But from where did these particles' energy arise? Hawking's solution was astounding. He suggested that the energy was seemingly tapped from the mass of the black hole, and as the particles escaped, the mass of the black hole steadily decreased until it completely evaporated away to nothing. But that wasn't the end, for if the black hole's information was written inside it, where did it go as the black hole evaporated? It didn't appear to be written onto the particles that were ejected, and physicists couldn't accept that the information had been erased. So they hunted for another solution. What if the information was not carried into the black hole, but instead was left elsewhere? Perhaps, they suggested, information was imprinted instead on the event horizon. As things fell through, this information could then be aired onto the escaping particles as the black hole evaporates, with the total information released into the universe as the black hole completely disappeared. And so, in this picture, the black hole is a three-dimensional object filling three-dimensional space, but it stores its information on a two-dimensional surface, the event horizon, in the same way that a hologram holds a three-dimensional image, all encoded into a two-dimensional surface. And some physicists have suggested the entire universe is structured the same way. Before we leave the importance of symmetry in physics, there is one more thing to explore: the fact that the symmetries of our universe cannot be totally perfect. Some of the symmetries have to be imperfect, have to be cracked, for if they weren't, we would not be here. Take, for example, the asymmetry of matter in the cosmos. The universe appears to be stuffed with electrons, many orbiting atoms, some just floating out in space, but their antimatter counterparts, the positrons, are comparatively rare. Extremely rare, in fact. Within the Milky Way, scientists estimate that they make up no more than a quadrillionth of the amount of matter. And so this raises the question, where are all the positrons? You might wonder why this is important, but it's really just another question of symmetry. Imagine the processes underway in the very early universe at the time when matter was created. If the processes were purely symmetric, they would have made equal amounts of matter and antimatter. For every electron that was created, a corresponding positron would also be created. After the fiery birth of the Big Bang, these equal quantities of matter and antimatter would annihilate, and this complete annihilation would leave nothing behind but a featureless soup of radiation. With no matter, there would be no atoms, no stars, no planets, no people. The universe would simply settle down into a featureless nothing. So there must have been a break in the physics of matter creation, a tiny asymmetry of 1 part in a billion that left 1 electron for every billion annihilations, as well as protons rather than antiprotons, and neutrons rather than antineutrons, leaving behind the matter from which we are made. Physicists are not quite sure where this crack is hidden in their theories, and perhaps they will need a theory of everything for this to finally be revealed. But other cracks in symmetry are apparent, and these might be providing clues to the ultimate nature of these asymmetries. The culprit is the weak force, the strangest member of the fundamental forces. Unlike the other forces, the weak force seems to distinguish between matter and antimatter. To understand this, let's start by thinking about a single hydrogen atom. This simplest of elements comprises a positively charged proton at its nucleus, which is orbited by a negatively charged electron. When this electron jumps in its orbit, it absorbs or emits a particular pattern of light. But what would happen if we considered instead an atom of antihydrogen? This would be a negatively charged antiproton orbited by a positively charged positron. When the positron jumps in its orbit, again a pattern of light is absorbed or emitted, and this pattern is precisely what is seen for normal hydrogen. This shows that electromagnetism is symmetric when considering matter and antimatter, and the same is true of the strong force, and even gravity. But not the weak force. The weak force is not symmetrical. The outcome of reactions is different depending on whether they take place with matter or antimatter. And this is strangely tied to one of the universe's most mysterious particles, the neutrino. The neutrino only interacts via the weak force, so it's always a player in weak interaction. What makes the neutrino bizarre has something to do with one of its fundamental properties, and that is that all neutrinos spin the same way. This is a quantum property, and quantum spin comes in quantized amounts. They do not literally spin. Photons of light also possess spin 1 unit of it in quantized amounts, and you can think of spin being right or left-handed. As the photon travels in our universe, we see both left-handed and right-handed photons. But the same is not true for neutrinos. All neutrinos are left-handed, while their antimatter cousins, antineutrinos, are right-handed. And this differentiates the interactions between matter and antimatter. But why do the neutrino and the weak force differentiate between left and right in the universe? Physicists still don't know the answer. But this crack in reality appears to have been essential for our very existence. Without it, everything would have been completely annihilated in the opening seconds of the cosmos. We've come a long way in this description of the rules of reality. We've discussed quantum fields and broken symmetries, warped spaces, and cracked symmetries. But there is one final example that shows how truly bizarre the quantum world really is when you follow its rules to the very end. Look up at the night sky. The light you see from distant stars is detected through electrons in your eyes, exchanging photons with electrons from millions of light years away. For 2 electrons to experience the electromagnetic force, they excite a vibration in the photon field. This photon travels between the 2 electrons, communicating force. But how do the electrons decide that they would exchange a photon and experience the electromagnetic force? You might think that one electron generates the photon vibration, which randomly impacts the other. However, this is not how quantum mathematics works. For the photon to be exchanged, the electrons have to agree one to emit and one to receive. But how can they agree, as they only communicate through the speed of light, through photons? Looking at the mathematics, it all becomes a matter of interpretation. In what is known as the transactional interpretation, the electrons communicate a handshake between the electrons that is part of the photon exchange. But to achieve this, the electrons exchange these handshakes through time. One electron sends its handshake into the future, the other into the past, and with a mutual agreement, the photon is exchanged even across billions of light years, and, one day, even trillions. But this need for time travel as a fundamental piece of reality is too much for some, who dismiss it as a mathematical convenience that masks something more fundamental. And so, where does this actually leave us in understanding reality? From holographic universes to wild mathematical implications, we now find ourselves at the philosophical edge of science. And what science even is it a search for the truth, to uncover the ultimate nature of reality? Or is the best it can ever do to give us a mathematical approximation, a representation of a true reality that is forever hidden. Your thoughts race as your mind tries to process this complicated picture. But suddenly your confusion is pushed aside as another thought snaps front and center in your mind. If nothing is real, then just what are you? Where do your thoughts reside? Where are you? About the ship of Theseus, over the centuries, time and travel take their toll on the aging vessel, and constant maintenance and repair are needed to keep it afloat. Eventually, every plank and every nail, every string of thread and yard of sail has been replaced. Eventually, no original piece of the ship of Theseus remains. The philosophers of ancient Greece pondered whether this is still the ship of Theseus, and if it wasn't, when did Theseus's ship stop being Theseus's ship and become something else? It might seem that discussion about a legendary ship is little more than philosophical musings, but the ancient idea has some profound implications about the reality of you. How old are you? If you cut yourself, vividly red blood will flow from the wound. But is the blood that flows from your veins the same as when you were a child? Just how long does a red blood cell survive? Made deep in the dark marrow of our bones, a red blood cell lives a mere 4 months before it's broken down and excreted from the body. Every second, about 5 million red blood cells meet their ultimate demise as freshly made cells flow into your bloodstream to replace them. Your body completely replaces your blood 3 times a year. Indeed, almost all of your body is eventually broken down and replaced. Your skin is replaced every few weeks, and for your internal organs, it might take a decade, but they too are eventually replaced. Whereas your bones regenerate over about 15 years, you are literally not the person that you used to be. Every one of us, and all living creatures, are biological ships of Theseus. And so, are you still the same you that was born? Are you the same you even though your individual cells have been replaced over and over? Unlike the ship of Theseus, if you are not the original you, when did this transition occur? And if you are not you, then just, what are you? What makes you you? The location of the mind, the seat of consciousness, has long been mysterious. To the ancient Egyptians, the heart was the center of all activity. It was home to the soul, with thoughts radiating out to the bodily extremities. This confusion arose out of a problem, thinking about thinking. Just what is a thought? Descartes decided that the brain and the mind must be separate things, coexisting and interacting within your head. Gottfried Leibniz supported Descartes' view on the separation of brain and mind, asking you to imagine him shrunk smaller than the size of a flea. At this minute size, he then invited you to join him on a tour of the brain. As you wander around, there would be no sights of thoughts within the fleshy material, no ideas bubbling away inside all of the biological machinery. No, he said, the mind is something separate, something distinct from the brain. But with the coming of the 20th century, Descartes' dualism came under attack, for advances in technology and biological understanding began to look at the working brain. Real-time mapping revealed that Leibniz's fanciful journey might be blind to seeing thought, not due to anything mystical, but because thoughts, whilst apparently physical, are invisible to the naked eye. The secret to the mind was electricity. With sensitive mapping, it was discovered that the brain pulses and bursts with electrical activity, with certain sensations and feelings lighting up different parts of it. It was realized that the brain is a highly convoluted network, more than 80 billion neurons with myriad interconnections. Signals trigger new signals that flow throughout the network. Electrical activity surges and cycles, builds up and dies away. But though it might be satisfying to think that the mind is just messy electrical signals, many mysteries still remain as to just how it works. Where is thought? Where is love? Where is creativity and imagination? Just how the brain works is a puzzle, a clouded enigma. Indeed, even the great brain of Einstein was remarkable for being unremarkable, stolen from his skull during his autopsy. Focus has since grown on the complexity of the neural network inside our heads. Maybe consciousness and thought are a result of this complexity, an emergent phenomenon that can't simply be revealed by exploring the network more than the sum of its parts. Emergent phenomena have often confused and bemused scientists. Indeed, emergent phenomena have often mystified many. There's a famous story of a Soviet aide visiting London in the 1980s. wanting to seek out the person who organizes the bread production in the city. In the Soviet system, bread production was centralized, with every step controlled, yet in cities like Moscow, long queues at bread shops formed due to inefficiencies. In the West, there was no bread czar managing production, yet an effective system had emerged from many workers performing their own tasks. It was reminiscent of an ant's nest. If you watch such a nest, many thousands of ants scurry about, seemingly with purpose. But no one ant controls the behavior of the colony. Instead, complex emergent phenomena arise from each ant following a simple set of rules. Indeed, emergent phenomena can be found all across the physical world. Water is nothing but a collection of molecules attracting and repelling through electromagnetism, but a body of water can flow and bubble with turbulent eddies and swirls, emergent behavior from simple rules. The physical properties of matter and gases also emerge from simple rules, and some now wonder if these simple rules themselves emerge from even more fundamental phenomena. Perhaps gravity emerges from truly fundamental pieces of space and time, in the same way that properties of water emerge from the interactions of molecules. And so, could it be true that the reality you experience, the world of wonders inside your head, is just the result of some complex wiring? Some find this conclusion unsettling. But for others, the notion gives them hope. If consciousness is just the result of complexity, not something beyond the physical domain, then maybe we have the hope of recreating, if not exceeding, consciousness. Indeed, this has been the goal of artificial intelligence for many decades, to build ever more complex networks, both virtual and physical, in the hope that intelligence emerges. There is a branch of physics known as synthetic intelligence that plans to put this to the test. This is unlike artificial intelligence, where people are trying to make computers think. Instead, in synthetic intelligence, physicists are building complex nanowire networks, wires that act like neurons and connections in our own minds. They hope that electric currents pulsing through these wires would represent electronic thoughts, and that these nanowires, which have the ability to reorganize, will have the ability to remember. This, of course, sounds like science fiction, but we might be only a few steps away from the dream of thinking machines. Of course, for those who cling to Descartes' dualism, this is nothing but an empty quest. As for them, no physical mechanism could ever think in the way that humans do. But for the believers, it is all just a question of time and complexity, and one day their networks will become aware, become alive. But if consciousness is purely physical, then deeper philosophical questions begin to emerge. If physical processes are really playing out in the fleshy pulp inside your skull, what if you were a brain in a vat, being fed stimulation from a virtual reality? What if you were not a physical brain at all, but just software executing on a computer? And what if Descartes' dualism is right, and consciousness truly exists beyond the physical world, a more ethereal plane where something like a soul resides? This opens another philosophical question, one that might be even more challenging for the idea of reality. Why should consciousness and thought be constrained to being human? What if it was much more widespread than that? What if consciousness is everywhere? It sounds again like we have entered the realm of science fiction, but this notion of a ubiquitous consciousness, of panpsychism, has been discussed by prominent philosophers. Consciousness that inhabits all corners of the universe. That everything, people, trees, rocks, sand, dust, stars, galaxies, black holes, everything is conscious. Molecules, atoms, protons, quarks, and electrons. Even the universe. This idea was beloved by some philosophers but is too much for physicists to stomach. Philosophers tell them that it somehow links with the weirdness of quantum mechanics, but physicists simply feel that this is well beyond the bounds of what they class as science. And, as ever, both groups tend to ignore each other. And so, could everything be conscious? Is reality alive? Your scientific mind ponders on this for a moment but concludes it a step too far. And so, you turn your head and look over once again at the apple. It fills your focus as your brain processes all the aspects of reality that have crossed your mind. You wonder about the apple from its entirety to its fundamental pieces, and as you think about its existence and its reality, you wonder if the apple is contemplating yours. You start to ask yourself if your thoughts on reality could get any weirder. Of course they can. Picture a scientist. What image pops into your mind? For many, It will be the wild-haired Albert Einstein later in life, with a wrinkled face, perhaps with his tongue sticking out. Or maybe Isaac Newton, in his formal regalia and 18th-century wig. But these images are of the great scientists many years after their seminal works. The alleged comedy show The Big Bang Theory has shown us that science is a young person's game, and although the awkwardness that is played for laughs is an unhelpful scientific stereotype, it is correct that most scientists make their biggest breakthroughs when young. Indeed, it's important to remember that Einstein was only 26 during his miraculous year. Isaac Newton was also a young man when he had his greatest insights into nature, and in 1666, he was just 23. He had already proved himself as precocious and had been studying at the University of Cambridge, but this year was to be a year like no other. The Black Death had returned again to Britain. The bubonic plague first raged across Europe in the 14th century, but it had never really gone away. For centuries, it resurged and cut a swath through European populations. With its re-arrival in 1666, people fled the cities for the relative safety of the countryside, and Isaac Newton left Cambridge for his family farm in the village of Woolsthorpe in Lincolnshire. As death stalked the land, Newton found solace under his famous apple tree, and his mind turned to unraveling the secrets of the universe. We've already met Newton's ideas of space and time, but let's look at time again. With his equations of motion, Newton could calculate how things changed with time, and time could be neatly cleaved into three distinct pieces: a past that had gone, a future that is yet to come, and an instant that is now. Reality, it appeared, existed at this unique instant of now a precise and exact, now evolving from its state in the past to the present and calculable into the future. But Newton's equations are purely deterministic, and so, if we had perfect knowledge at any time, we should be able to calculate the exact state of the universe at any other instant. And so this raises an interesting question. In a Newtonian universe, has the past really gone? Is the future really unknown and yet to come? In some sense, the realities of the past, present, and future all exist, and the instant of now is just sliding through this already complete history, with us just experiencing a moment of reality. This idea returned with a vengeance in Einstein's theory of relativity. Instead of just a background, space and time became central to the story, with each fundamental particle tracing out a distinct path, its world line through these four dimensions. And like Newton, Einstein's universe is purely deterministic, with past, present, and future all existing. This came to be known as the block universe. Once again, the mathematics is pretty clear on something quite bizarre. The equations of relativity are unequivocal. Einstein's universe is a block universe. With perfect knowledge, there is no mystery about the future, as it can be calculated from now. In fact, Einstein's equations don't just define what now is, you have to define when now is. There is nothing special about now in Einstein's universe. Of course, the block universe raises some uncomfortable questions. Questions around free will. The ability to choose between possible options seems innately human, but in the block universe, this is just an illusion, as the future is already written. And the block universe also has even bigger consequences that stray back into science fiction. If the past and future are out there in the block universe, could we ever reach them? Out there, Da Vinci, dinosaurs, every creature, and everything that will ever be. And maybe there are convoluted space-time paths that mean we can experience them in our now. But the issue is that the block universe just doesn't feel real. Surely the future is unknown and yet to come. And so, many tried to look beyond the raw theories of Einstein to provide an answer. Eventually, the probabilistic nature of quantum mechanics appeared to show that Einstein could not be correct, the future being written only from the possible outcomes of quantum questions. And so, the picture that emerges from this compromise is that the universe is a block universe, up to a point. And that point is now. Now is constantly being constructed as quantum questions are answered. Now adds another sheet of reality to the block universe, unfolding an unknown future in front of us, with the past solidified into the block behind us. Interestingly, this is the picture offered by loop quantum gravity, one of the contestants for the theory of everything. Within this theory, space and time are constantly being weaved from fundamental loops. Now is the edge of the weave, the past is the tapestry, and the future is the unknown ahead. Our reality, our now, would be at the busy edge of the construction of space and time. This gives you pause. Is the apple you see now the same apple you saw just a moment ago? Are its time, space, and fundamental constituents constantly being knitted from the ultimate fundamental? Are you and the apple being rewritten at every single instant you experience, deconstruction after deconstruction? Your grip on reality seems to be definitely slipping, and so you settle on a simpler question. Where is reality? Maybe reality is the block universe, and that's all there is. Maybe free will is an illusion, or maybe loop quantum gravity is correct, and reality exists as an instant of an unfolding universe. But what if there is something much deeper underlying reality, something that is not physical? What if, at the bottom, reality is nothing but numbers? This idea isn't as strange as you might expect. Indeed, it reflects our understanding of the workings of the fundamental universe. Written at the heart of all physical laws is the notion of information and information processing. Just what do the laws of physics do? Well, they take what we know about a particular situation, the information of that situation, such as the location and velocity of a ball flying through the air, and process it into the information of that scenario into the future. This is probably most apparent in the rules of quantum mechanics, where the information of a scenario is encoded into the wave function. The rules of the quantum evolve the wave function, the information, into the future. Numbers are churned into new numbers as the laws of physics are played out. This all might sound a little esoteric, but by the mid-20th century, strong links had emerged between information and thermodynamics, as it was realized the effort to process a signal requires energy. A computer has to expend energy to flip a bit from a 1 to a 0, or vice versa, as does your brain as you process even the simplest of thoughts. All of this has led some to propose that everything is really just information processing, that there is no fundamental difference between the processing of information on a computer, the processing of information in your mind, or the processing of physical information that underpins reality. This is the foundation of what is known as the simulation hypothesis. This hypothesis states that our thoughts, memories, and all our experiences are nothing but computations. This is deeper than the idea of a brain in a vat that we encountered previously, as there is no physical brain. In fact, in our reality, there would be nothing physical at all. Of course, the simulation hypothesis raises an immediate question. Just where would these computations be taking place? Perhaps they exist in a higher reality, a physical domain that we can know nothing about. But what would be the goals of our simulated reality? Why would our creators create us? What if we are little more than characters in a game of The Sims? But that's not all. What if the simulation was not created for us? What if it was constructed to explore other aspects of synthetic universes, and we are nothing but an unexpected side effect? What if the creators know nothing about our existence and care even less? Of course, we can argue about all these questions, for the answers might always elude us. But here on Earth, physicists do generate synthetic universes with the goal of understanding our reality, and also explore other, seemingly hypothetical universes where the laws of physics are different. Maybe one day, with powerful enough computers, conscious creations may inhabit our synthetic worlds. But even if we are living in a simulated universe, and our reality is completely synthetic, surely our creators would inhabit a real reality, a physical reality. And so, have we just pushed the problem upwards? Or is it turtles all the way down? We come to this conclusion because we imagine that there must be a physical computer, a device that carries out the calculations that construct our reality and synthesize our universe. But what if there isn't? What if there is no physical basis for reality? What if there are only calculations? This is the idea of the mathematical universe. The lead proponent of the mathematical universe is Swedish-born Max Tegmark. In his earlier research, he focused on the challenges of modern cosmology, but eventually he turned his attention to some of the biggest questions we have. His mathematical universe is similar to that of the simulation hypothesis universe, but without the need for a physical computer to do the computations. And so, where would these calculations be performed? What would be performing them? Surely you need a computer to compute? But being truly fundamental means that these mathematics just exist, and there would be no real answer to where they came from, or where they exist. Intriguingly, Tegmark's mathematical universe is actually a multiverse, containing not only our universe but all possible universes. In the growing maelstrom of mathematical calculations, there is not only our particular reality, but all possible realities, each defined by distinct mathematical structures of their own. Across this multiverse, there should be mathematics similar to our own, with multiple versions of you, whatever you really are, out there. Of course, there will be other universes quite different to our own, different in terms of the strengths of the fundamental forces or dimensions of space and time. The library of possible mathematics is immense, possibly infinite, and definitely much larger than the subset of mathematical structures we use to describe our cosmos. So, out there in the sea of fundamental mathematics, there could be much, much more. Not only universes we have not dreamt of, but many we could never dream of. And one last horror. One prospect of reality exists in this mathematical universe, and it is time to infinity. Every so often, within the infinite sea of calculations, just the right calculations will randomly come together. These calculations will look just like your mind, a mind filled with your memories and reality in just an instant. You will be created maybe considering an apple. Of course, to this brand new mind, with all its memories, everything seems completely normal. They remember the big events from their lives, picking the apple from the tree. But the existence of this mind is only temporary, only a mathematical fluctuation. As quickly as the mathematical structure of this mind came into being, it vanishes back into the wash. This consciousness, with experiences of reality as real as ours, is doomed to disappear in an instant. And these relatively tiny fluctuations in the mathematics would massively outweigh the likelihood of our entire cosmos. And so, how do you know that you are not one of these minds that will vanish in a moment? How do you know that anything you think is real was there a moment ago? How do you know that you are not about to wink out of existence? By now, you might be thinking, well, this is ridiculous. I know that I'm not a mathematical structure. I remember what has happened to me. There's no chance that I'm a temporary existence. I know that I am truly real. But unfortunately, getting rid of the mathematical universe does not fix the problem. It is believed that our cosmos has an infinite amount of time ahead of it. And for this infinity, the universe is going to be cold and empty, long after the last star has died and the final black hole has evaporated into the background. And so it might seem that we would reach the end of the story of the universe there. Not a lot will happen in our future empty cosmos. Surely it will be a quiet, uneventful place. But this future universe might not be as dead and buried as it might seem. And to understand this, we need to explore one of the most misunderstood concepts in physics: entropy. Ludwig Boltzmann was one of the most insightful minds of 19th century science. Before it was widely accepted, he was a supporter of the atomic hypothesis, the idea that at the smallest level, matter is made of indivisible atoms. He recast the laws of energy flow thermodynamics in terms of the motion of these indivisible atoms. Boltzmann's view attracted criticism from the scientific greats of his time. But shortly before his death in 1906, direct evidence for atoms began to appear. In pondering the realm of atoms, Boltzmann wondered how they could be arranged. Think about the air around you, atoms of nitrogen, oxygen, and carbon bound into myriad molecules. These molecules are whizzing about, colliding with each other, with the walls, and with you at every moment. Every configuration of atoms and molecules seems completely indistinguishable, but experience tells us that the atoms are unlikely to spontaneously gather in one corner of the room. And if we started with all the atoms of air in one corner, they would rapidly spread out and fill the room. Boltzmann showed that this difference is simply a matter of statistics. Specific atomic configurations evolve into more general configurations. This evolution of configurations from specific to general is known as the growth of entropy, and it has become one of the most fundamental rules in the cosmos.